Morning, guys. So, hi, folks. My name is Aoyu. Today, my colleague Raphael and I will present our work on understanding and optimizing srsRAN for low latency. We're from the Laboratory of Sensing and Networking System at EPFL. So, first, I would like to shortly introduce our lab. We're based at EPFL in Lausanne, Switzerland, right next to the beautiful Lake Lemont. So it's very beautiful. Here is our lab. And here are the main members in our lab. So our lab is led by Professor Haitham Hassadio, and we have one external expert, Dan Mihai Dumitru, who is also here. And we also have 6 PhD students, including me and Raphael. So our lab focuses on 3 research areas, including wireless imaging and sensing, next generation cellular networks, and Internet of Things and mobile systems. So both Raphael and I are working on next generation cellular networks, which will be the main focus today. So now, in the era of 5G and even future 6G, we have many emerging next-gen applications, from industry automation, rescue services, to extended reality. And all of these applications share the same future. They all require low-latency communications. And back to release 18, 3GPP for the first time proposed a concept ultra-reliable low-latency communications, which defines 0.5 millisecond requirement for both uplink and downlink one-way transmission. And in recent discussions around 6G, people even push this requirement to 0.1 millisecond. And however, until quite recently, it's not clear where does latency come from in real-world 5G systems, and what bottlenecks do theoretical and simulation work overdo, and can we mathematically model these bottlenecks? And finally, can we fundamentally bypass these bottlenecks? So, based on the srsRAN project, we will present 2 main work from our 5G research. The first one is AI-based predictive uplink scheduling, which we use AI to bypass uplink scheduling bottlenecks to reduce user plan latency. And the second one is system-level latency modeling, where we use mathematical models to capture complex latency behaviors in real-world 5G systems. So to begin with, I would like to recall the main bottlenecks in uplink scheduling process in 5G or even next year. So as shown in this figure, we have UE connecting to a GMD. And once the UE has uplink data to send, it needs to first sending a scheduling request. Basically, the UE needs to tell the GMD, okay, I have some uplink data, I want some grants. So after receiving the SR, the GMD must go through radio processing and protocol delays. And here the radio delay includes the time spent in radio head, like SER, and is in the action with the visible layer. And the processing delay consists of the time required for layer 1, layer 2, decision-making, that processing. And the protocol delay is introduced by 5G standard and system configurations. So in our lab, in our recent 2 papers, we have went through these delays in detail. So if you're interested, feel free to take a look. So then, the GMD sends the srsRAN, actually the first srsRAN, to the UE. And this srsRAN is really small and fixed. And for example, in the srsRAN project, it is 500 terabytes by default. And from some paper, in some US commercial operators, they even use 2 to 3 result blocks, which is small and fixed. And after UE receiving the srsRAN, the UE will send a small amount of data up to 500 terabytes, appended with a buffer status report, BSR. And this BSR reflects the actual amount of data in the UE buffer. And then, after the GMB receiving this BSR, this report, the GMB needs to go through radio processing protocol delays again before sending the first BSR grant. After receiving the BSR grant, now the UE can finally transmit a large amount of data. And starting from this point, the Jimmy becomes buffer-aware static. So from this figure, we can see that there are two startup latency segments. The first latency segment setting the SR, waiting for the first SR breath. And the second latency segment setting the first BSR and waiting for the first BSR breath. And in the default configuration of srsRAN project, these two startup latency segments are 10 milliseconds in total. And these uplink scheduling bottlenecks arise from a fundamental challenge, that is, the Jimmy has no knowledge of the UE buffer. As this is very different from the dotting scheduling, where the Jimmy has good knowledge of the UE buffer. And this also makes the whole uplink scheduling process much more complex, and will be our focus. So far, we have talked about grant-based access, which is the default approach in srsRAN project, and it's usually quite efficient, like in that point, because the Jimmy allocates exactly the amount of resources needed by UEs through these SR, BSRs, but it comes at the cost of high latency, exactly because of the two latency bottlenecks we just mentioned. So another approach is grant-free access, where a UE is pre-allocated resources. So once the UE has uplink data to send, it can directly use a pre-allocated grants to send the data. It doesn't need to wait. It doesn't need to go through SR and BSR. And this helps reduce latency, but it wastes resources when there is no data to send. So it will lead to low efficiency. And as we can see here, the two approaches lie at opposite extremes. So a natural question to ask is, can we achieve something in between these 2 points? And here comes our proposed solution. We propose to predict future uplink data arrival time and size. So by predicting the arrival time, we aim to remove the need for scheduling requests, and thereby removing the first latency segment. And moreover, by predicting the arrival size, we aim to remove the need for BSR, and thereby removing the second latency segment. So, here's our vision. Through our proposal, we aim to combine the benefits or advantages of both worlds. We want to achieve low latency benefit from grant-free access, and we also want to achieve low inefficient benefit from grant-based access. And to perform the prediction, since we want to use AI predictors, the first important step is to find the prediction target, that is, what we want to predict, or what we will offer as input to those AI predictors. The straightforward starting point is to use the signals already available in 5G systems, which are the buffers that record BSR, as we introduced before, and the service data unit, SDU. And here, the SDU represents actual payload size delivered over the video link, which is sent from the map layer to the RS layer. And exactly at this point, we can intercept its value and infer the traffic dynamics at the UE side. And as shown in this figure, after we have 5K uplink data arrives at the UE side, the UE presents an initial BSR, then an SDU of 4,000 bytes, followed by a second BSR. Actually, it will follow by more SDUs and BSRs. So can we use these signals as prediction targets to AI predictors? The answer is yes. However, they have important limitations. So the key issue is both signals are tightly entangled with system dynamics, for example, vehicle bandwidth, MCS, or channel policies. So a single uplink arrival event at the UE side can trigger a sequence of BSRs and SDUs. And if we see the right figure, except the first BSR, the values of all subsequent events will change as soon as the system dynamics change. Here, maybe the channel bandwidth is half, or the MCS is half, or the channel policy becomes worse. So this limits the generalizability of AI predictors and require a large amount of training data to cover various system dynamics. And moreover, this can result in an increase in inference time, as now we may need a big model to cover all these dynamics. Do we have a better option? So here in conclusion, we can think of the 5G as a future. So traffic arrives at the UE side, it goes through the whole 5G filter, so it will shape what the GMB sees. So a better choice, we use the concept of traffic arrivals, which can be computed based on the following equation. So basically, when we have two consecutive BSRs, we will add the current BSR to the total SUs in between and subtract the previous BSR. So this can tell us how many traffic has arrived in two consecutive BSRs. So in this example, we can see that there is no traffic arrival between the two consecutive BSRs because based on the equation, VNU equals to 0. However, this is only an ideal case. So in reality, the BSR is encoded in discrete levels. That is, if the value of a BSR falls within a specific range, it will be considered as a semi-index. Like for example, in the first example, when the value of BSR falling from 30.9K to 4.4K, it will all consider index 20. And moreover, as more data arrives, this discretization becomes more obvious. Like in the second example, if a BSR falls within 39K to 55K, that's a big gap, it will all be considered the index 27. So what's the consequence? As shown in the right figure, exactly because this discretization, it will hide small changes in the EE buffer. So as a result, even when there is no actual traffic arrival, the GOP may consider or interpret as if traffic has arrived. So basically, in the second example, exactly because the two consecutive BSR has a semi-index, so the GME thought there are some bytes arrived at the site. And we refer to such traffic arrivals as ghost arrivals. So, overall, a single uplink burst can trigger multiple real or ghost arrivals. So why do we also have multiple real arrivals? Because the traffic arrival process is not instantaneous. They may last of several milliseconds and span multiple consecutive time slots. So maybe at the first uplink slot, we have 1.5K, the next one 1.5K, and all of us on those arrivals. So all of these factors will distort the inter-arrival statistics of the traffic application traffic and will trigger unnecessary back-to-back predictions. And this makes the prediction process both inefficient and inaccurate. So motivated by this, we propose the concept of traffic checks. The high-level idea is to group tightly spaced traffic arrivals into one single traffic trap. And so here we have 4 arrivals, so we have one traffic trap, and this traffic trap will be separated by trend detection threshold. It defines as a fixed number of consecutive idle uplink slots, which means this trend X. And this threshold can be application or slice dependent. So for example, a small battery can be used for URC traffic, which is usually sporadic and small. And the bigger battery can be used for eMPP traffic. So with this concept, we aim to map each uplink burst to a single traffic trap. And this concept can help us to preserve the bursting nature or inter-arrival statistics of application traffic. So now we only need to perform one prediction for uplink burst, making the process both efficient and accurate. After defining the prediction target, we still face 2 fundamental challenges in the system design. First, there are various emerging next-gen applications, each showing different traffic features. And second, the next-gen systems had strict tuning constraints, where a single time slot can be as short as 60 microseconds. It is therefore difficult to use one heavyweight general AI model for all applications. Just imagine if you want to consider a new application, you need to retrain the whole model again. So we propose to use multiple lightweight dedicated AI models optimized for different applications. However, a key question that remains is how we can assign these AI models to their corresponding applications, since we have multiple lightweight models. To achieve this, we propose a traffic-aware model database that contains multiple traffic profiles. Each traffic profile consists of a pair, a statistical feature vector, a lightweight dedicated prediction model. So when a new application joins the network, we will construct a query vector using its statistical features, like mean, max, and so on. Then, we will use this vector to query the model database. So specifically, we will measure the logarithm distance between this vector from this new application and all stored traffic profiles statistical feature vectors. And assuming this example, the best match is traffic profile 1, which corresponds to the dedicated prediction model 1. So now we have the answer. Then we will retrieve this prediction model for this application in an online manner and perform predict uplink scheduling for this application. And the whole model database follows a plugin design. With this design, new entries, if you want to handle a new application or if you want to remove an entry from the application, you can easily add it or remove it from the model database without affecting existing applications. Now, we're ready to go through the system design, which consists of 4 nodes and 5 components. The 4 nodes include the GME, real-time rig, near real-time rig, and model database. So in component 1, the GMB forwards traffic data, which is time series, to the near real-time rig. And the near real-time rig constructs a query vector, as we mentioned before, and retrieves a prediction model of the best match from model database. And this model is further sent to the real-time rig for future operation. And in component 2, the GMU verifies the model's performance by tracking its prediction error, because it's very important to decide if we can trust this model. And in this component, the GMU continuously requests the real-time rig to perform AI inference. Basically, the GMU will send the traffic data time series to real-time rig to submit these AI tasks, and the real-time rig will forward back the prediction results. So, if the model's performance is good enough, which means the model passes the verification, the GMB will perform proactive uplink resource allocation. Specifically, it will use a predicted traffic trends from the real-time rig to allocate uplink resources in advance. And if the model's performance is not good enough, which means the model does not pass the verification, the GMB will ask the real-time rig to perform online continuous learning. So specifically, the real-time rig will update the model weights incrementally by 1 epoch supervised learning. By doing this, the real-time rig will adapt the model to the current traffic behaviors. So finally, we also enable runtime and external updates to the model database. So the GME can replace the new real-time rig to train a new model on a large dataset and insert this new entry in the database in an online manner. And all network operators thus can prepare new models offline and add them to the model database without affecting the whole system, without any downtime. So we can request the model database to scan the new entries periodically. So here, I want to present our evaluation across various applications from surveillance cameras, mobile AR, SLAM, CS2, Google Meet, WhatsApp, industry automation, SCADA system. And all experiments are done through real-world testbed. So here the baselines are grant-based access, we introduced before, and grant-free access. And for grant-free access, we assign the whole physical bandwidth to a single UG. And we can see that our proposal consistently achieves lower latency and high efficiency, which means it takes benefits of both access approaches. And we hope our work can inform the design of future AI-driven NetG systems. One interesting to mention is the uplink traffic can be challenging to predict. For example, in our experiments, we also try Zoom and Team432. For Zoom, we use dynamic FPS, dynamic bitrate. And for Team432, it's really dependent on the players. So in such cases, network operators can assign the UE to grant-free access, and which is very different from grant-based access. So the key question is, to guide this access, how can we define a good grant size? So we have developed an NLAP model So specifically, if you see the x-axis of these two figures, for each possible branch size, we can compute the corresponding analytical latency and bandwidth consumption. And we have implemented this model in the real-time rig, which helps determine a good prop branch size for this application. So basically, when we have a new application, we will only assign the new application prediction model. We will use a predict IP scheduling when the model is good, can be trusted. Or we will just give a good branch size. And now I will hand over the talk to my colleague Raphael, who will introduce this model in more detail.
Thank you, W. As my colleague discussed, we needed a model to understand the effect on latency and throughput when assigning different amount of resources to different traffic. And so, we started by looking at existing models, like the MATLAB 5G Toolbox or the NS3-based 5G Lena. Unfortunately, we quickly realized that they did not match the range nor the shape of the latency distribution of srsRAN. And even trying to match all the parameters, we realized that they cut corners, and this did not allow us to replicate the same exact configurations that we were running in srsRAN. We also did some literature review, and we found that very few papers tried to break down the latency in the 5G RAN. We tried to code them, but again, we observed that they oversimplified the system, and their estimations did not match the real-world over-the-air latency that we were observing with srsRAN. And thus, we set off to build a model of our own. And we could quickly achieve a model that would match the latency distribution of a single configuration. But as soon as we tried to generalize it to match any configuration, we quickly realized that this was far from trivial, and primarily due to three challenges. First, 5G allows hundreds of parameters to be configured, and it is not clear which one among these have an effect on latency. Moreover, there are interdependencies among these parameters, either due to the specification, to physical constraints, or sometimes even due to implementation choices. And finally, not all these parameters show monotonic behavior, meaning that it is not enough to simply set them to their lowest value. And while we were developing this model, we realized that it would be helpful in many more domains than simply choosing the appropriate run size. For starters, this could bring some insights on what is still preventing 5G from achieving EROC. My colleague talked about this at the beginning, and I will have a more detailed slide towards the end. But 5G aims at achieving sub-millisecond latency. And yet, if we look at real-world deployments, we observe latency values that are more than 10 times higher than this. And not only that, but initial thoughts around 6G seem to indicate that they are targeting even lower values, as low as 0.1 millisecond. This work can also be used to optimize a configuration given a set of constraints. We hear more and more about private 5G networks which are not operated by commercial operators. There is one upstairs. And of course, we cannot all know about every single parameter. Even the srsRAN configuration reference is now quite a big document. And thus, it would be helpful for the community to have a tool that would allow optimizing a configuration given a set of constraints, be them spec-related, liquid requirements, implementation choices. This work could also be used by congestion control algorithms to make better, more informed decisions when adapting the congestion size window, and avoiding to treat the inherent 5G latency as a sign of congestion in the network. And finally, this can be used in elaborate joint communication AI applications that need to make rapid decisions regarding their edge offloading. And to show that it is not as trivial as simply setting every parameter to their lowest value, we can take the case of the TDD period. One might think that reducing the TDD period necessarily reduces the latency. But this is not always the case. And in fact, we can show that with the default srsRAN configuration and with the minimum min K2 value, moving from a TDD period of 2 milliseconds to to a TDD pillar of 1 millisecond does not reduce the latency, and in fact, it actually increases it, due to the interaction among the different offsets and parameters that will delay the grant allocation, which will subsequently delay the uplink data transmission. And thus, with this in mind, we set off to build our system, and with the goal to equip it with two main components. First, a latency solver that could find the latency distribution of any configuration and that would be able to simulate different traffic distributions. And all this by accounting for the non-determinism of certain parts of the system. And second, we decided to develop a configuration optimizer that would take any set of restrictions as input and that would be able to come up with the best set of configuration parameters to achieve the lowest possible latency. And we wanted it to be fast because we wanted to run it live, and thus we made it highly parallelizable and with a detailed routing phase. To develop our model, we studied the interdependencies of the different parameters and components. And we started with the simplest case of a single ping packet, which does not create any congestion and which can be transmitted in a single OFDM symbol. Subsequently, we incorporated the more articulated and elaborate cases, but for the sake of simplicity today, I will refer to the single ping packet. And now, even for a simple ping packet, the journey is quite articulated. And to capture all of the dependencies, we introduce some general variables that contain the different phases. For example, W1 shows the time that Aoyu has to wait until the next scheduling request opportunity. Similarly, W5 is the time between an uplink grant is received and the time in which an uplink data can actually be transmitted. On the other hand, W3, W6, and W7 relate to the processing delays in the GMB. And thus, W1 through 7 recap the uplink transmission latency, while U1 through 4 make up to the downlink transmission latency. And in this way, we split the problem into computing these general variables. Now, coming to the results. And in this figure, we show in red the over-the-air real-world latency that we measure, while in blue, we have the one estimated by our system for that particular configuration. The different graphs show different scenarios, such as different TDD patterns, different SR periods, as well as different traffic types, moving from synthetically generated like Gaussian inter-arrivals all the way to real-world zoom and DOTA2 traces. They mostly show the uplink latency, as this was their most complicated one to get, but figure F shows a downlink latency distribution, and they're all based on SRS, except for figure E that compares it to the OAI latency. You know, these figures kind of show that the distribution kind of look the same, but to quantify the quality of our estimations, the Earth moving distance or Wasserstein distance comes in handy. This is a commonly used metric in statistics that shows the amount of work needed to move the mass to move from one configuration to another one. And thus, lower Wasserstein distance means closer distribution, so lower value, the better. Although it is hard to say which one is a good value because there are different ways of normalizing it. And so, the best way to show that these are actually good values, it is to compare it to the related work. And in fact, when comparing it to the Wasserstein distance of the related work, we can in fact see that they are low values. I mentioned that we wanted to account for the non-deterministic components of the system. For example, there are some processing delays at the UE and the GNB side, which do not always take the same amount of time. And so, we collected a large amount of data, and we empirically fit the best matching distribution to such parameters, turning them into running variables. And with this, we observed that we were able to substantially lower the Earth moving distance or Wasserstein distance by better matching the real world over-the-air distributions. Now, I hinted at the URLC requirements at the start, and they are defined by the 3GPP as 0.5 millisecond one-way latency for both the uplink and the downlink directions. Well, now one might agree or not with these requirements, deeming them realistic or not. But nonetheless, we used our tools to estimate how many among the possible configurations would be able to achieve such tight requirements. And so these two tables show the amount of configurations that are able to achieve 0.5, 1, and 2 milliseconds with 50, 90, and 99.99% reliability. The one on the left uses the radio latency that we were able to measure on our real-world SRS SDR-based testbed, while the one on the right uses a very optimistic negligible radio latency. Finally, so far we've only been considering the single in-packet case, which does not create any congestion and which does not have to deal with any contention. But we also wanted to model the more complicated cases, and we discovered that congestion breaks the temporal independence among packets, and thus we were no longer able to come up with a single closed-form mathematical formula. And for this, we developed a finite state machine that would allow us to simulate and evaluate the latency under congestion and contention. Now, of course, in this case, more complicated things come into play, like the map layer scheduling and the RLC buffer queues. And with this, I'd like to conclude our presentation. I want to point out that we are committed to open sourcing our work. So at some point in the future, we will upload our stuff on our website that you can reach via the QR code. And I want to thank my colleague Aoyu for being here with me today, and our friend Arman, which unfortunately will not be here due for visa issues. Where have you today in any pressure?
I apologize that you mentioned this and I didn't catch it. When you talk about real data, how did you, where did you put that point from?
It's from the real applications. I mean the AI part.
But what in real application?
So real application is based. Yeah, basically we have real world testbed, we have real UEs. So we run these real world applications, for example, Google Meet through the real world UEs, and we can get the traffic data.
So this was not the wrong testbed. This was not from like this.
Yeah, it's not from the virtual operators.
Collected, yeah, over either SRS or VoIP. Because
That was that, but with the mobility, what was it that?
Currently, SAP is.
I have a couple. Yeah, we pretty really nice. Very, very nice. Very. So this traffic aware thing that you make it in near papers, you don't really have visibility.
So you don't know the draft. So how did you understand what kind of traffic you're dealing with?
So maybe I could take this one. We did not yet go via the standard E2 route. So we had a near real-time rig of our own that we developed, and we designed our own interfaces. And so we were able to copy a lot of the traffic over and directly work on traffic. And that
At a big PU collect.
when we got collected the standard like mean, max, average.
So as well as like for example, let's say we have automated traffic versus robot traffic versus electric traffic. So what's the difference in the terms of metrics?
But the packet size, the IRI, but it's the packet size, yeah,
The bus, yeah. I said so are not really available.
over the standard Twitter page of it. Yeah, that's why we decided to go our own way for that. Because
We did a paper called Tractor, a PDRSK. So they developed this deep learning models to actually classify it roughly to the T2 KDI.
yeah, I think we check it out.
Yes. But the second question I have for you is, you also did something similar which I never published because you were heavily criticized that a single base station have thousands of users, right? In the internet. How can you maintain 1,000 models in a single base station, right? So we call it happiness aware. Some user model, the idea was that you just get enough RVs to a user depending on what application they use, that curiosity, some kind of machine learning, and said, okay, if you're browsing up, just give me 40 RV, but if you're doing AR, then I'm gonna give you 50 RVs. And then we just make sure that you're always there, you're happy. So that's why we call it happiness aware model, right? So in your case, right, again, you rely on this user prediction, which cannot scale. But so again, the idea first is that we don't have a model for every UE, but for every application. So in these thousands of UEs, likely some of them are going to run the same applications, like sensors that are going to report the same thing. And now this is for the model database. Whereas for the running in live, we were also scared about running AI at such low, like the TTI is 1 millisecond, half a millisecond. And actually something that also comes from the Linux Foundation is ONNX, which allowed us to run AI model like, I'm not sure what's the correct term, but we turn the models into some ONNX runtime, which are extremely fast and predictive. Have you looked at some real data sets? So we also wanted to analyze to some extent. We look at this data set from Brazil or somewhere. We could not generalize every user's behavior, even though they are doing the same applications. We had about 6 applications in that data set, like YouTube, browsing, and stuff. It would not generalize across different users. Yeah. So the way you basically have end users and application that's time into end models.
Right. The way we use to generalize is the continual learning. So maybe they are not exactly the same, but they kind of do the same. So a bunch of the people retrain allow you to fine-tune the model to work. For what kind of data set do you work with for your work? I think we can take it offender. We have a game or 9 couple sets. I know. So there's some kind of data set or you collected, okay? Some we collected and some were that is obvious. And also is one thing interesting mention is, so basically if you observe these traffic dynamics from a high level point, like at time scale of 1 second, maybe some are hard to distinguish. But if you observe these traffic dynamics at a time scale, like a time slot level, you can consider it a microscope. So actually the traffic features will become more obvious. Yeah, she can make problem easier to classify. And you also mentioned the scalability. Actually, we try to populate our model database with synthetic like 10K entries. And actually, even with 10 entries, the whole retrieval process can finish in 100 milliseconds. So it's still very fast. And regarding when we run these AI tasks, like AI inferences, we also design an AI task scheduler in the real-time week. So it's very similar to the concept of age of information, like based on the urgency of different AI tasks. Like for example, based on the arrival time of this application, its traffic, and also the inter-arrival statistics to handle this capacity. Yeah.
Please. So what question I have is it? Say should be something that's based upon like a pre-based slice as compared to a course. Yeah, it's basically a big answer. De fato, das so fact of these days based on it, they optimize or the other Jesus are yeah, right. So we get let's say your goal is at this, for set portfolio.
So basically, as we show in the system design, we have 4 components for the GMB to extract these traffic trends. And the real-time rig will handle all these AI tasks like the real-time inference, real-time continuous learning, which we represent model in our next format, which can be very fast. So for example, when we have a small model, we can run model in like 100 of microseconds. And for the near real-time rig is more extract these time series just to feature vectors. And we have also a database to store all of these entries. So basically, it took some time.
So for the list, like, yeah, what? These much ways.
So we use the quectal models, discrete modems that you can connect to a Linux system and control them very nicely. We also try phones, but phones, they tend to send a lot of background data and start to isolate them. So we tend to use discrete models, either quectal, syncom, Sierra.
So it allows to define at the verified
To make the the Linux running a Linux kernel allowed that, like when we are generating the traffic, to really timestamp them, and then we were able to synchronize it very tightly to the UKF or the GLB regime via like a TTP backhaul, so we could really accurately measure one-way latencies. But this was kind of a big. At first, it was hard to make accurate one-way measurements.
So maybe like more so. Basically, we try some existing tools measure one-way uplink latency, but it didn't give us a very exact very good results. So what we do is we design our own measurement tool. So basically, when we use a band latency from the 5G modem, it has like the interface on the E modem side, and also the interface of EPF, or the exit interface anti-tune. We use a Kubernetes ports. Yeah.
You mentioned the ability of this work to kind of help guide future applications of the band model survey architecture. So I missed maybe up the church takeaways on lessons learned for how to architect or records the data or types of data that go ahead and access to.
Yeah.
So basically, your question, you want to know how can this inform future? It's a very interesting question. To me, the person thinks we're working with this real-time system is somehow limit the size of these AI predictors. So we cannot like these large language models use very general big models. So first, we need to define a good input, like a good matrix to input to these models, which can be more efficient and accurate. That's why we propose a concept of traffic trends. And also the second one, can we, instead of using one general model, we use these multiple models so that we can just retrieve the model online and use these very lightweight models in a timescale of 100 microseconds. So is that the future of these energy systems? So, and the third is actually, you see this model database. We want, in the future, possible different groups, different companies, they can try this model database. So not only one group doing this to fill in new entries in model database, maybe different groups can share their different entries. So it's really like if you want something you haven't tried search online or from another group, you just add their entry to the model database and directly retrieve them online, directly incorporating your systems. That's what our is.
So assuming that the way your vision works as a wish, and the deploy is in a network. What is the ultimate? I mean, what's the bottom line? What is the network going to see at the end of the day out of this technology? Is it better throughput? Is it better? I mean, other network.
So as a network level, first our main target is to first reduce the user plan latency, because we want to bypass these two startup latencies. And secondly is we want to also get more scalability or want to improve the efficiency. And this is about the traffic uplink scheduling part. And more visions about these model databases can we think a new way to share AI models in the network systems.
But am I going to see a better capacity of the network? Am I going to see a better faster response for gaming or something like that?
Yeah, so
what am I going to see at the high level? Forget about the...
Yeah, sure. So basically, you see from our evaluation, we can achieve lower latency. We can see lower latency, like 10 milliseconds even more, as a direct result.
So I guess for application, the latency is critical.
Exactly. Especially for the use cases in private 5G networks. Yeah, that's...
So you track one wireless type, set the gauge theory, profit here too, that if I have few guys that want will they see access to the system and they're competing for that access, is that not a different auto to support kind of
Yeah, so of course, contention is going to play a role here. So you can run these models and you can assume that you have enough resources to give to everybody. Now, if this is no longer the case, probably there's a root cause. Why did you admit that these main users if you don't have enough resources with them? So then you can start thinking about slicing, offloading, and there are different... So what we envisioned here was assuming you had enough resources to fulfill the SLAs that you give to the application. Maybe... I'm not sure if I got your question right.
Well, it's good answer. I guess if you had enough resources, would I just do grind free?
Yeah, so the idea was that compared to run-free, we are more efficient. So you can admit more users than simply doing run-free. And then, on the other hand, we have lower latency than graph-based. So we were trying to close the triangle. Compared to graph-based, it would be more efficiency compared to front-based, lower latency. And also here, I see has seen about the scenario where you have multiple slices. So basically, you have a low latency slice, which you will guarantee the latency or improve the latency through our proposal. But since now we can save some resources, you can assign these saved resources to some best ever slice. So for common use, you have more resources to use. It's not only about we only have one slice and we assign all of them to grant free. Yeah, that's also kind of that scenario.
So from what I understood, you did some end-to-end Isaiah scaling very for viewing GPA. My question is, how big was the card that was not the bad layer? If you did any analysis on that, because there's buffering, reordering timers, and things like that. So did you get any analysis on that, or?
Yes, so we ran some analysis with very lightweight traffic, which ideally did not have that much buffering to the higher layers. And so that's how we learned about the protocol delays of waiting for an SR, waiting for the correct moment to send. But of course, yes, the MAC layer is quite important when you start having contention and congestion, and the scheduling algorithm plays a big role, because you can have like just a stupid scheduling algorithm that delays traffic frequently, right? So, and then the RFC buffer. So yeah, there's the larger the packets, and the more these higher layers come into play. But for us, it was more interesting looking at the lower layers and seeing simply what even a lightweight packet can experience, because that's where we wanted to cut.
Rush. Okay, thank you, Ron.
Thank you.